All right. So, hey guys, I'm not exactly sure. I think I'm in the frame here, but it's been a minute since we kind of did a technical update, so that is what I'm going to do here. So understandably, not a lot of people know how to code. That's what we're doing. So this should serve as some sort of update to be like, well, what are we working on, and where are we at, and where are we going? So I think what would be interesting is to talk about the smart contracting language that we're building. So we, in our white paper, in our technical overview, we talked about using this language called PACT. PACT is cool. It was developed by some guys out of pt1, and it's Turing complete. Now, the good thing about PACT is that it's out of the box. You can just kind of plug it in, plug and play. The bad thing is that it's written in Haskell, which is a hard language for most developers, let's say. It's a very special breed of people who program in Haskell. It's closer to, in terms of like, formal verification, I guess I could say, which is like how do you derive something to math, so you know it's going to work the way it works. So the security attack vectors, closer to formal verification, the better. So we started poking at it. We got this guy downstairs who's working on it, and he kind of picked through it, and he's a Haskell guy, and he's kind of like, I could dig this apart and kind of get it to do what you want to do. But as I was looking at the syntax of PACT2, basically they wrote it in Haskell, which is like a super hip language. And if you program, you understand that. And then the syntax is Lisp, which is equally as hip and as like, it's a very hipster language, right? It's like a craft beer, a very, very hoppy craft beer. Not everybody likes craft beers. That's okay. But the craft beer people will say that their craft beer is superior in every way. But there's a time and place for everything, right? Lisp, confusing for most people, right? It's just weird looking. It doesn't really make sense. It goes against a lot of different kind of paradigms that we're used to today. And so I kind of was like, well, our smart contracting dev can spend just as much time tearing through this and kind of modifying it to what we're doing, or we could think about looking at how do we program a DSL. And a DSL is a domain-specific language. Domain-specific language means that it only encapsulates a certain domain. It does not go outside that domain. So if you can establish that domain, you can essentially say, okay, our security is like this. A perfect example would be CSS or HTML. CSS only exists to essentially create the styling for web pages. Nothing more, nothing less. That's great because that's what it does, right? It exists inside the browser container. It can't go outside of that. Domain specific, right? HTML, same sort of thing. HTML is never going to be able to do anything outside of what the browser container allows it to do. It's limited by that domain. Something that's not a domain-specific language would be Python, right? Python can do anything to your system. You can put it into microcontrollers, you can put it into database structures, you can make web apps out of it, machine learning, people can write new software that interacts with like the processor all the way up. That's as open as it gets, right? And so one of the things that's kind of a criticism of the EVM is that it's more closer to that because that's Turing complete, allows smart contracts to do literally anything that you can't predict the security attack vectors, right? And so if you can produce a DSL where you understand what people are doing and it exists inside a very limited scope, it's very well defined, then life's good, right? So that's kind of what we've set out to do. Instead of what Ethereum will do, like we haven't really seen any other sort of smart contracting systems come out that are, well, our chain is new, and they basically are doing the same thing, but they have a new virtual machine. It's in my opinion close to Ethereum, where they've done some syntactical stuff on the front end of the programming interface to say, hey, we fixed this hole. But there's still going to be attack vectors because the core is still way too powerful and can do anything. So smart contracts exist in a domain over here. EVM covers this massive domain. Right, so smart contracts are a very particular thing. In the world of things to program, we have games, we have smart contracts, we have websites, we have machine learning. The EVM, in theory, can model all of this stuff. It can. If we're not talking about gas and we're talking about coding all this stuff, yeah, it would be ugly to make a game in Solidity. It'd be really bad. But you could do it in a very, very disgusting way. It works best for smart contracts, right? Because that's what people use it for. But it's this broad. Similarly with anything that's going to create a virtual machine that tries to emulate a computer. I mean, you don't need these things. We already have known that what do people want when they're using a smart contract is generally ownership, right? It's either saying, I own this particular thing, I have this much of this thing, I want to pass the rights to this thing. Another interesting thing that I think is going to appear that isn't really used yet is RBAC, which is role-based access control. And this is like keys, right? So the idea that you have a public ledger where you're keeping track of different types of entities. So like for a law firm, you're going to have some structure where you have the big dudes on top, right? And then they're going to have their paralegals, and then they might have like their office workers, right? Now, if you have a legal document that comes in, right, into the law firm system, you only want certain people who have certain roles in that organization to actually be able to sign that document, right? So you can assign all these people in your system, office workers. All these in your system, paralegals. All these need to be lawyers, right? So we can have supersets, right? Obviously these people, unless it's like, you know, an invoice comes in, right? We're gonna say this is like, I don't know, some sort of like, it's a real estate document that a lawyer has to sign off on. Not that big of a deal, right? You don't want your office workers doing that. Paralegals, sure, they can sign off on that, right? Let's say it's a really big legal document. It's very important, and the paralegals don't have the nuance and expertise yet to understand it, and so the law firm doesn't want those people to sign off on it. Well, you can essentially understand what's going on. Supersets, right? Of the rights of people who can sign things. This is the lawyers, paralegals, and then office workers. Now these types of models, Ethereum's not really designed for this. They do have some sort of like, there's like some new things coming out, but like, CSA, I think it is. The key library for producing keys for signature verification is a very sort of, it's not focused upon in Solidity, so you don't see a lot of applications doing this. However, you know, it's not that you can't, it's that a lot of people don't. our goal here is to identify this sort of solution along with what people are actually using Ethereum for, and then create a domain-specific language for modeling those things specifically. You're not going to do physics. If you want to learn, if you want to model gravity and solidity, you can. You definitely can. It's going to be a pain in the bum, but you can. We're going to cut that off. You don't need gravity, right? If you need to calculate gravity, do it on your front-end machine. You don't have to do it on the blockchain, right? So we start to see these different like domains appear. The eraser is missing. So I'm using a napkin. So we have ownership, access control, and some sort of like object, I guess, right? That we want modeling. That's about it at this point in time. We haven't really seen anything beyond these things. So an object being like a token, ERC20 tokens, you know, or some sort of like tradable asset like CryptoKitties, ERC721 object, right? And now access control, right? But a much deeper level of access control that's ingrained into the system rather than how Ethereum allows you to do it, but it's definitely not tuned for that. And then this idea of ownership and passing ownership. Again, Ethereum didn't include this in what they were producing. The way by which you pass ownership from things became a standard developed by Open Zeppelin in their ownership solidity contract later on. I don't think it was actually thought about when they were designing the language or the EVM. It comes down to the EVM. People say, oh, Viper's going to solve it. Viper's not going to solve the bugs in the EVM. You're always going to be able to do those attack vectors until you change the EVM, which I don't know if that's going to happen, at least anytime soon. So, what we really landed on is instead of, let's say, EVM, and we're calling this Seneca, because Seneca was a Stoic philosopher, and I identify with this Stoic concept of pragmatism and kind of absolving yourself from emotions and looking logically and rationally at things. We have some sort of code, right? So this is called grammar, right? And it's called grammar because it's sort of like language, right? And a language has grammars. So you have some sort of grammar. We're calling this Seneca, right? This solidity boils down into operations called opcode. And what that opcode does is it boils into the EVM, and that turns into essentially state changes. And now the difference here is these operations, like on your computer, when you open up a program and you allocate memory, that's doing operations. So you're literally allocating memory onto this thing. And when you're doing that, there are tons of attack vectors. I mean, Intel just, that massive release of like their backdoor or their bug or whatever, I mean, it's down to a processor level when you're allocating memory in this way. This is like a computer, world computer, right? We're not really looking at that. You have Seneca. Instead of opcode, this boils down into database queries. So you can have some basic logic, right? You can have if statements, you can have else, no loops, no jumps, nothing. It's not really code, it's just enhanced SQL. And so what this does is when you're basically compiling or interpreting a contract, it could say if balance greater than 0, do this, else do that. And at compile time, all it really does, like from the delegate standpoint, is do these checks because the delegates have the current state. And then based on that, it either outputs this or it outputs that as essentially database changes, and it broadcasts those database changes and confirms with everyone, hey, is this accurate? Yeah. Bueno, perfect. So by doing that, it's not actually a programming language, it's not actually compiling. It looks like it is, but it's not. It's all about data access. Everything else you can abstract from the front end. Everything else, like, you know, the math, the whatever, even down to some of the logic, right? The actual logic should exist on the front end rather than the back end. This is merely for key storage, switching ownership between assets, moving things around, and having that public identity verification. So we need to constrain the order of things and say, this is what this is for, this is how it's going to work. If you balloon it too much and you treat it like a computer, computers get hacked. You can't really hack data. The only actual attack vector that can exist is if you write bad code. And if you write bad code, there's nothing you can do. But for a lot of these EVM attacks, they are bugs that never even existed, like compiler bugs, where the operation code is being calculated in an insecure way. So a developer doesn't even know that that's going to happen. They're like, what? For this, database queries. You're selecting data, you're updating data, that's it. You're not doing anything more. Here, it's not about the data, it's about the operations. So you can literally take advantage of the nuances of the, you know, the binary data, the memory location, the allocation of actual memory. And there's a lot of attack vectors there, and that's very bad. This is a little higher level, so, you know, it wouldn't even really matter what database type you use, because you can take these database queries and turn them into equivalents, like, oh, update the records for Pete, his balance has gone from 0 to 100. You can describe that in SQL, you can describe that in MongoDB's language, you can describe that in Redis. They're all different, but at the end of the day, what has to happen is Pete has to have his balance updated. And that's it. That's all you say. Pete has to have his balance updated, update that. And as long as consensus can occur on that level, you're fine. You're fine. Consensus does everything. If people misinterpret one of these codes, their current state will be off and they will fall out of consensus. So the idea of potential failure in other implementations is a real thing, but it is not something that is a existential threat so much. I think, like in the EVM, it's a lot easier to mess up one little thing, and that cascades up because it's such a complex system. If you mess up, like, oh, this is supposed to indicate a select query and it doesn't, pretty easy to know that, because this boils down to SQL and SQL type languages. There's not much you can screw up. You either screw up the query or you don't, and there's basic control flow. As long as you have a test suite there and everything's okay, and you have 100% code coverage, and you test every single step, you say, okay, great, bueno, life's good. Even with the EVM, if you do that, a unknown error can occur because of the compiler or in the EVM, because just like computers, we don't really know all of the nuances because the dimensionality of it's so large, and that's scary. And that's why you always hear about these new data breaches and hacks and things going on down to like a hardware level, is because we just said, do everything. And on a personal computer, that's fine, right? Because it's like, the worst thing that can happen is your computer's toast, which is one singular person, right? But when it's a global database, well, a world computer, we're looking for a global database. Millions of other people's dollars are at stake. So hundreds of millions of dollars have already been lost by this system, this EVM, just destroyed. That's crazy. That's crazy. And it's something that can't occur if the true adoption of blockchain is to happen. If we're ever going to, everyone says this whole crypto thing is kind of thrown up in the air and everyone's just seeing where it lands, but it's been in the air for so long that you're just like, where is it? Well, where is it going to land? If it lands and it doesn't actually do anything, it's game over. We really only have so much time with this whole experiment before someone wises up and takes advantage of this. We have a brief moment in history to really capture this. And yeah, it's just a matter of time before U.S. government comes in and says, all right, we got our own system. And everybody starts using it because we have the fiat and we have the money supply and we can just switch it over. And it's convenient because people care about convenience. Your grandma does not care about this. She wants to buy groceries, right? And so the floof is fun. But we need to be serious about the actual application and how this is going to work. World Computer, great. We learned something from this. It's time to move on towards a more restrictive model so people don't feel like they could lose their money essentially in the system. If an attack occurs, you're toast. And in most of the attacks, it was completely unannounced. The DAO attacks, the smart billions, they had it coming. But also the parity hacks as well. I mean, those could have been prevented just by better tests. I mean, so yeah, it's time to get serious about this stuff, and there's going to be a lot more development and like some tactical stuff that is going to be presented. But this is also not a small offering. This is a very big thing to do, and so expect progress, and expect progress to steadily occur. It's not happening tomorrow, folks. We got a minute and a half, maybe, before this stuff actually comes up with fruition. Of course, with my methodology, it's lean, right? So it's like build a skateboard, but you want to build a train, to move people. So we can have a skateboard, right, of this language out much quicker. You get a board, you put wheels on it, you put casters on it, it goes, right? And then we can work towards a train. That's kind of the model, right? So you can expect that. Still got to build a skateboard though. So I hope that gives some idea about what this is and the philosophy behind it. This is not a gimmick. I think people also say, oh, just make your own smart contracting language because it's hip and cool. Okay, I think people who aren't following or are not developers and do not actually understand the nuances or the history of what's going on can't appreciate something like this. And that's fine. That's fine. But we're not here to appease those people. We're here to actually make real, credible results that people globally are going to use. There are technologies that power the internet right now that you have no idea about. Apache.